Welcome to this lecture series in linear algebra. In this lecture, we'll prove that eigenvectors, non-zero eigenvectors corresponding to distinct eigenvalues are linearly independent, and all we need is just the definitions, primarily. All right. So here are some problems for practice, and now let us get started. So here is our main theorem that if T is an endomorphism on a vector space V, we are not assuming anything about the base field, it's just some arbitrary field. Then we claim that non-zero eigenvectors of T corresponding to distinct eigenvalues are linearly independent. Okay. So what we will do is we will prove this, but in special cases, and then I will show you the general proof. So first, let us prove it for two eigenvalues. So let lambda1 and lambda2 be two distinct eigenvalues. Just 1 second. Okay, we have two distinct eigenvalues of T, and let us pick two non-zero eigenvectors. So pick V1 and V2 such that this is the case where these two are non-zero. So what have we done? We had two distinct eigenvalues. Corresponding to lambda1, we have picked a non-zero eigenvector, and corresponding to lambda2, we have picked a non-zero eigenvector. And let us show that, want to show that V1 and V2 are linearly independent. Okay. So let's see why. Suppose not. So say, or even let us not even go by contradiction. So say alpha 1 V1 plus alpha 2 V2 equal to 0 for some scalars alpha 1 and alpha 2. And if we end up showing that both of these are 0, then we are done. Both of which are 0, both of alpha 1 and alpha 2 are 0. Then we will have shown that V1 and V2 are linearly independent. So fine, we have this equation. Let us label it. Let us call it something. Let us call it star. And let us apply T on both sides. So applying T on both sides gives us T of the left hand side equals 0, which implies that because T of alpha 1 V1 is equal to that and T of alpha 2 V2 is equal to that. Okay, let us call this dagger. All right. And now by star, we are just basically multiplying lambda 2 to both sides of star. So lambda 2, or maybe let me write it this way. So alpha 1 lambda 2 V1 plus alpha 2 lambda 2 V2 equals 0. What have we done? This was star. We multiplied both sides by lambda 2. That's it. And let us call this something. Let's call this clubs, or I like to call it broccoli because it looks like broccoli. So by this and that, if we take the difference of these two, what do we get? These two together imply that alpha 1 times lambda 2 minus lambda 1 times V1 is 0. So just take the difference. This minus this is equal to 0 minus 0, which is 0. But what is this minus that? That is equal to this thing, because we take the difference of these two terms and these two terms cancel out. So we get this equation. Now lambda 2 and lambda 1 were different, so this is non-zero. V1 was picked as a non-zero vector. So if alpha 1 is such that, or rather I should say, we have a non-zero vector whose alpha 1 scale is 0, it forces that alpha 1 must be 0. This gives alpha 1 is equal to 0. And similarly, or in fact, once you know alpha 1 is 0, you get alpha 2 is also 0 by this equation. So this also gives that alpha 2 is 0. Or you could repeat the reasoning for alpha 2. So we have proven this for two eigenvalues. You pick two distinct eigenvalues, corresponding non-zero, two distinct eigenvalues are picked, corresponding non-zero eigenvectors will be linearly independent. Let us repeat the proof for the case of three distinct eigenvalues. It will be a very, very similar proof. So here let lambda 1, lambda 2 and lambda 3 be pairwise distinct eigenvalues. Alright, and again we will pick non-zero eigenvectors for each of them. And we want to show that v1, v2 and v3 are linearly independent. Okay, so again, say some linear combination vanishes. So say this is 0 for some alpha 1, alpha 2 and alpha 3, and we want to show that each alpha I is 0. And we have called this equation star. Again, apply t to both sides to obtain this equation, which gives this equation, which we will label as dagger. Alright, fine. But like in the previous page, we will multiply this by lambda 3 on both sides. So we get by star okay, and call this broccoli. Okay, so we have dagger and broccoli, so we just take the difference and this term will cancel out. So we will get by dagger and broccoli, we get by taking the difference alpha 1 lambda 1 minus lambda 3 v1 plus this thing is equal to 0. Okay, and now this is a non-zero field element. This is also a non-zero field element because lambda 1, lambda 2 and lambda 3 were, sorry about the typo, lambda 3 were pairwise distinct eigenvalues of t. So this is non-zero and that is non-zero, and hence these two are non-zero eigenvectors corresponding to lambda 1 and lambda 2. Right? Any scale of an eigenvector is also an eigenvector, and since this is non-zero, this is also non-zero. So the upshot is these two are non-zero eigenvectors corresponding to lambda 1 and lambda 2, and hence by the previous proof, those two are linearly independent. And since this linear combination vanishes, the linear independence implies that alpha 1 and alpha 2 must be 0. So the proof for the linear independence of 2 gives the proof for linear independence of 3, since once alpha 1 and alpha 2 are 0, by star alpha 3 must also be 0. So that finishes the proof for 3, and the general case can be proved by induction using the same reasoning. So let me show you the formal proof. So this is the first page of the proof, and this is the second page of the proof. You can pause the video and look at the proof. Okay, and this has nice consequences. So first consequence that this is the main consequence that we draw. If T is an endomorphism on an n-dimensional vector space, then T has at most n distinct eigenvalues. It cannot have more than n, because if it had more than n, you would produce more than n linearly independent vectors, but that would contradict the dimensionality of the vector space. So that's that. And as a consequence, we have a very nice fact that if we have an endomorphism on a vector space V, then there exist two invertible endomorphisms such that T is the sum of the two. So every endomorphism can be written as the sum of two invertible endomorphisms. For instance, 0, the endomorphism 0 can be written as the sum of these two invertible endomorphisms, where this is the identity. So why is this? Well, here we need the infinitude of the field. So assume the base field is infinite. At least for the proof we will need it. So for instance, you can take real or complex or rationals. So let's try to show this. So we have been given T, an endomorphism on V. There are only finitely many eigenvalues of T. So pick some lambda which is not an eigenvalue. So pick a lambda which is not an eigenvalue. Then write T can be written as T minus lambda I by 2. Let me write it in a slightly different fashion. So that is how we write T. And if lambda is, So pick a lambda such that neither lambda nor minus lambda is an eigenvalue of T. That can be done because the field is infinite and there are only finitely many eigenvalues. So pick a lambda such that neither lambda nor minus lambda is an eigenvalue of T. Now we write T in this fashion. This equation is obviously true. And now note that this is invertible because lambda is not an eigenvalue of T, right? The non-invertibility of T of this endomorphism is equivalent to lambda being an eigenvalue of T. So since lambda was chosen so that lambda is not an eigenvalue of T, this is an invertible endomorphism. And by the same reasoning, by the choice of lambda, this is also invertible. So you can express T in this fashion, and hence this proposition holds. So that's very nice. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.